Hello everyone, my name is Helen Koike and welcome to this presentation about image signal processor, ISP drivers, and how to merge one upstream. A little bit about me. So I work with Collabora since 2016, and which we are an open source consultancy company. And I'm mostly working on the kernel, mainly in the media subsystem. I also have experience in other subsystems such as NVMe, ALSA, device mapping, and here and there in general, but mostly inside the media subsystem. Right now, I am the maintainer of the RK ISP driver that we're going to talk a little bit during this presentation. And I'm also the maintainer of the virtual media controller driver. I am really proud to say that I was an outreach intern in 2015, where I started the Vink project there. Laurent Panchard was my mentor and who proposed this project. And right now I am the co-coordinator of the Linux kernel project in Outreach, together with Vaishali, who is the current coordinator. So if you have any questions regarding this program, or if you want to become a mentor, so feel free to reach out. The main goal of this presentation is to give you an overview of the camera ISP memory pipeline. Then we are going to give another overview about the media framework, some design choices when implementing our driver, also some lessons learned when I was upstreaming the RK ISP driver. And I also want to talk about this specific user space tool called Libcamera. So I hope that this presentation is going to be useful for those who are not entirely familiar with the Video for Linux community, but want to get started and upstream their own ISP driver in the subsystem. Okay, so let's start with the camera ISP memory pipeline. On your phone, usually we have the camera, and this camera is composed by a sensor. This sensor is composed by smaller light sensors that's represented by this gray grid on this image, which comes from Wikipedia. These gray sensors, they are sensible to light, and on top of it there's a filter, a color filter that only allows a specific color to pass through. Which means that the set of it is basically a color sensor. And the readings of all those color sensors is sent to your computer, to your SoC, processed in some way, and the image is made available to your application. So what is an ISP? An ISP stands for Image Signal Processor, and the common use case is that the ISP receives the readings of all those small color sensors and transforms it in an image that is usable for user space. It can also perform several other image transformations, such as format conversion, debayering, for instance. So the format with all those small color readings is that we call a Bayer format, and transforming it in actual pixels is the process that we call debayering. We can also convert to RGB, YUV, and several others. ISP can also perform crop, resize, white balance, compose, image stabilization, that we're gonna talk a little bit about it, effects, filters, flip, rotate, several others. So those are processing that's performed by the hardware, and it helps offloading your application so that you don't need to perform software. An ISP can also generate some statistics such as histogram, error contrast, and several others that they are used by application to implement algorithms that can read those statistics and reparameterize the ISP to improve the image on the fly. So some examples of those algorithms are histograms, histogram equalization, what we call 3A for autofocus, auto exposure, and auto white balance. What an ISP is not, so an ISP is not a codec. ISPs work with raw and uncompressed image, while codecs that we can divide into encoders, they transform raw image to a compressed image format such as H264, JPEG, or VP9, and there are several others. And decoders do the opposite. They transform compressed image into raw image, back to raw image. Now let's talk a little bit about different kinds of ISPs, so inline versus offline. Offline ISPs can be divided in two phases. One is retrieve the information from the sensor and place it somewhere in memory. The other one is getting this memory that's usually in a Bayer format and do some kind of processing and place it back in memory. Usually those two phases are implemented in two separate drivers, and communication between those two drivers is coordinated by user space. An example is the IPU3, the Intel IPU3, that is divided in IPU3 CIO2, the camera interface drivers that gets the image from the sensor and places it in memory. And the other one is the IPU3 image unit driver that processes this image and sends it to user space. An inline ISP is when the data reaches memory only in the end. So the sensor is directly connected to the ISP without touching the memory. Then ISP do some kind of processing and then it reaches memory for user space. One example is the RK ISP1 driver. This is not entirely true because this hardware can do both actually, but in the driver only inline is implemented. So we can have hybrid devices that can get the image directly from the sensor or from the memory, and it can behave as inline or perform the second phase of an offline ISP. One example is the MediaTek 8183 Pass1 driver, which is not yet upstream, but it is published in the mailing list. So the image can come from those two paths. So one is represented by the DMA input there, is the memory, and the other one is a connection directly from the sensor, so sensor camera interface. This data go to the binary processing and then it reaches memory for user space. MIPI DPHY, let's take a look at this. So MIPI DPHY is a very common bus used in the market for camera and displays. It is specified by the MIPI Alliance and it is a physical layer with high data rate that can process 4K image, so ultra high definition image, ultra high resolution with a really good frame rate. In this image there we have Raspberry Pi that is connected to a sensor through this flat cable bus. So this bus is the MIPI DPHY. This bus can have up to 4 data lanes, and it also has an I2C bus for configuration. So in this image on top, we have the camera connected with the host, and we have several data lanes, some clocks, and then the I2C bus. On top of this bus, we can have up to 2 protocols. So one is the DSI2 for display serial interface, when the computer wants to output image to somewhere, usually a display. And the other one is the CSI2, the camera interface, to capture image from somewhere to the computer, usually from a camera sensor. And this MIPI DPHY CSI2 is a really frequent term in the ISP land. So I mentioned this because you're gonna see these acronyms in some other diagrams during this presentation. Now I would like to talk about the RK ISP1 driver in specific because I have most experience with this and I will also use this driver as an example during this presentation. So the RK ISP1 is the driver of the ISP block that's present in the Rockchip RK3399 SoCs. These SoCs can be found in several devices, such as the Scarlett Chromebooks, which is the tablet in the image, RockPi boards, or Pinebook Pro laptops. The driver was originally written by Rockchip. It was merged in kernel 5.6 under drivers staging with more than 9,000 lines of code. So this is the hardware architecture of the ISP, the Rockchip. The image can come from those two buses. One is the MIPI DPHY that we mentioned, and the other one is parallel bus, but the parallel is not implemented in the driver right now. Then image goes to the ISP to perform some kind of processing. Then it goes to some image enhancement blocks, and the image can go to one of those two paths, or both of them at the same time. Those two paths can perform cropping, resizing, do some RGB, flip rotation also, and then it reaches the memory. The main difference between those two paths is the use case. When you have your phone and you want to take a picture, you can see there's a preview. And this preview is really fast. If you rotate, it can rotate quickly, and it is display ready. You can see that there's almost no delay. It's live preview, so it's really fast. And if you noticed, you can see that the resolution that it shows is usually not the full resolution that your camera supports. So when you take the picture, it will take a little bit more time, and the final image is a really higher resolution. So basically this preview would come in this case from the self-path picture, and the picture itself would come from the main picture path. So the main picture path supports a higher resolution. It doesn't need to generate RGB display ready images, doesn't need to flip, rotate, while the self-path needs to be fast for display and doesn't need to be a higher resolution. So one is fast and the other one is slower. The ISP comprises with image signal processing, many image enhancement blocks, crop, resizer, RGB display ready image rotation. And we have those two paths, so the self-path for preview and the main path for picture, as we mentioned. Of course, those are use cases. User space is free to use whatever it wants. Now let's take a look at the kernel side, the media framework. In the Linux kernel, in the media framework, there is this concept that we call topology. So user space can query a node inside DevFS, let's say /dev/media, some number X, to retrieve how the inner blocks of the hardware are interconnected and the order of the image processing. For instance, in this image, user space can know how those blocks and how they are connected. It can know that we have a sensor that is directly connected to the ISP that is connected to some DMA engine where the image reaches memory. In a topology, we have two types of nodes. So what we call subdevices in green, that represents the inner parts of the hardware. And user space can perform some configurations there. And the video devices in yellow, that represents the DMA engine, where user space can perform some configurations, but it can queue and dequeue buffers containing the image or metadata to and from the hardware. In this example, it is from the hardware because we are retrieving an image from the sensor, but we are going to see some other examples that the user space needs to inject an image into the driver or some kind of metadata. Those blocks are connected by what we call links, and links always connect pads. So those zeros and ones in the image are what we call paths. Some interesting thing to note is that usually the sensor block is a driver that is separated from the rest. This is because we can reuse the same sensor with different kind of hardware. So in my development setup, I have the same sensor that can be used with the Raspberry Pi that we saw in the previous image. But I use with the Rockchip board. So the sensor is the same, but the ISP driver is different. This is the topology of the IPU3 CIO2 driver, the camera interface that performs the first phase of the offline ISP. We can see here 4 blocks of the IPU3-CSI2 subdevice. It means that we have 4 buses, and we can connect. We can retrieve image from sensor for 4 sensors at the same time. In this case, we only have a single sensor, so the IMX355 that is connected to the first block, and the other ones are not connected. And the yellow blocks are where the user space is going to interact. So in this case, /dev/video0 to retrieve images from the kernel. The camera interface will place the image in memory in some format that is very specific to this Intel driver. So it is up to user space to get this image and feed to this other driver, so the IPU image unit that performs the second phase of the offline ISP. Then user space is going to retrieve the image from the previous driver and feed it to this first node there, the IPU3-Imgu0 input, to inject the image inside the buffer inside this driver. Then it will perform some kind of processing, and it will make the results available through one of those 2 paths. So we have the output there and the viewfinder. If I recall correct, those are the equivalent of the main path and the self path. So one is meant for the picture itself with higher resolution, and the other one is for preview to be fast. This driver can also generate some statistics through the node down there, so 3A stat, and user space can read those statistics and put some parameters on that node called parameters. So in this case, we have two instances of the ISP. It means that it can process 2 images at the same time. Here is the topology of the RK ISP1 driver, which is inline. In specific, this is the topology of the Scarlett Chromebook, which is a tablet, and we have a back camera and a front camera. Those camera sensors are represented by the top blocks, starting with OV, and just one of them can be connected to the ISP at a time. That's why you see one line is dashed. ISP performs some kind of processing, and it outputs the image through one of those 2 paths, so main path and self path, as we mentioned before. And this driver can also do something similar to the Intel driver, generating statistics and receiving parameters from user space. Now I want to talk about some driver configuration architecture that you should think a little bit about how you design your driver. In a specific case, auto versus manual configuration propagation. In the auto configuration scheme, user space will do all the configurations and operations on the DMA engine node, so in the yellow blocks there. When user space wants to set a resolution, it will set the resolution through the node/dev/video0, and it is up to the driver to propagate this configuration on all the blocks of the topology, including the sensor that can be a separate driver. So as you can see, the other blocks doesn't have any node exposed on DevFS. On the other hand, in the manual configuration propagation scheme, user space is the one responsible for configuring all the pads through all the pipeline, the image pipeline. So for instance, if user space wants to configure a resolution, it needs to configure a resolution that the sensor up there needs to generate on its pad 0. Then it needs to configure the same resolution to the ISP block in the pad 0 to inform the ISP which resolution it should expect from the sensor. Then user space needs to configure the resolution that the ISP needs to generate, and it needs to match the resolution that the resizer expects, and needs to configure the resolution that the resizer should generate, so could be bigger or smaller to zoom or shrink the image, and finally setting the resolution that is expected inside the memory buffer for the final image. As you can see, this increases a lot the complexity for user space since it needs to perform all those configurations, and if formats don't match, when you try to start the stream, it will fail. On the other hand, it provides you a finer grain configuration in the inner blocks of the hardware, and I'm going to show you an example when we need this. But also, the more blocks that we have exposed to user space, more complex it becomes, since we have more points that we need to perform the configuration. Also, manual configuration is extendable, since if we come back to the previous slide, we cannot mix auto and manual configuration. So if you choose one scheme, you need to stick with it. We cannot have a manual configuration on the subdevice, on the sensor block there, and auto configuration on the ISP. Doesn't make much sense. So if we want to add more blocks in the future and you chose auto configuration, then you realize that this new block could benefit from the manual configuration, then you won't be able to change it. Or maybe you could add some parameters when loading the driver, but then it won't be compatible with other applications from user space anymore. Why RK ISP is manual? To answer this, I want to talk a little bit about crop. So how do you crop the image? You just select a subrectangle in the main image of the sub-image that you are interested in. The media subsystem allows you to expose an API that allows user space to select a subrectangle on all the pads actually, but we are going to see that we could allow user space to select this subrectangle under the final node there /dev/video0, but we're going to see that we have some problems because this driver allows cropping the image from the sensor, so before doing the processing in the ISP, and it also allows cropping the image just before the resizer, so it can shrink or zoom a specific image. And exposing this crop only once in the final video node would be confusing for user space, since it wouldn't know which cropping the driver is using. So instead of exposing the crop only on the final node and allow auto configuration, we expose the API of selecting a subrectangle on the topology in specific paths to make it clear to user space where this cropping is taking place. So in this example, we allow user space to select the subrectangle on pad 0 of the ISP, so it can select which part of the image from the sensor it should work with, and also in pad 0 from the resizer, so you can select which parts should zoom or shrink. Now, about the image stabilizer, how it works. So usually we have the main image, and the image stabilizer just selects subrectangle in the main image. The idea is that only the outer rectangle would shake and not the inner one. So if you shake your phone, the image shouldn't appear that shakes that much. Just to relate a bit, when you open your phone, your camera, and you select the video mode, you can notice that the angle of the image shrinks a bit. It seems that it zoomed a little bit. It means that it's just showing you the subrectangle, it's not showing you the outer part, so it can have some space to work with. That means we need to allow user space to select another subrectangle. And we expose this one in the pad 2 of the ISP. So we have 3 points to select subrectangle. Then exposing this just in a single point and allowing auto configuration doesn't make much sense. That's why in this case we have manual configuration propagation. File subsystem. I want to talk a little bit about some design choices. This was the original topology of the driver when I started working with it. We had this block exposed, so Rockchip SY MIPI DPHY, and we removed it. And I'm going to explain you why. So this block represents the MIPI DPHY bus, right? In the manual configuration propagation, as we saw, if we have more sub-devices, more complex for user space. So we need to rethink a little bit more about which blocks we want to expose. And the file block there doesn't expose any image configuration, this just represents a connection point. Ideally, in the topology, the useful information is just the image processing steps. And also, the same processing steps could be used in different buses. In this case, the RK ISP1, it supports the parallel bus. It's not implemented yet, but could support, and the MIPI DPHY CSI2. So the idea is that one doesn't provide much information. So if we come back to the original topology, if we want to add support for the parallel bus, we would need to update topology dynamically, depending which bus you are using, replacing that block with the parallel block, which would be confusing for user space that needs to perform all the manual configuration, or we would need to expose another block to represent the parallel bus. And another block, more complex for user space. That's why we decided to remove it. Some lessons learned. If you have, so I see this and some other drivers that people post upstream, the code from the bus is usually integrated with the code of the ISP. So if you can separate those in 2 different drivers, one inside the media subsystem and the other one to the PHY abstraction layer subsystem under driver/PHY. Then with this, you will have a more generic topology for any bus. It is less complex for user space. And the ISP driver itself becomes much cleaner since you separate those 2 drivers. And the PHY driver can be used for other protocols as well. for DSI, for instance, if you can have both protocols under the same line. So some more lessons learned, not only in the technical perspective, but I also want to talk a little bit about the community perspective. The Video for Linux community is very open to accept drivers in staging, with the condition that you work on it to move it out as soon as possible. You also need to have detailed to-do list with requirements, what is missing from moving it from from staging. The advantage is that it make available to other people to use and also improves your workflow. It's much easier to get contributions from others if it is already upstream somewhere. Otherwise, people will need to send you patches directly to you, and you will need to integrate on your patch set every time and repost it every time. So it's much easier if it's already upstream. Also, it makes it easier for people to test, to send you bug reports. And it also decreases the maintenance costs, since you don't need to keep rebasing all the time, and you can work on it step by step with also the collaboration from the community, who can follow all the progressions. So just still about the staging, I really recommend you to do that, with the condition that you work to remove it as soon as possible. So some more lessons learned. Don't be afraid to reorganize the code. If you are going to maintain the driver, make sure that you feel comfortable with it. It has your way, right? So don't be afraid to change the files, namings, the code order, rewrite functions. Also, I would recommend splitting the code between different files per implementation node, so per block in the topology. Some cases this is not entirely possible because we reuse a lot of code from one block to another, but at least separate the code between the video nodes and the subdevice nodes, since those are different. They have different hooks inside the media framework, and it makes it much easier to review them if they're separate. Of course, those are all tips. Take it with a grain of salt. Check if those apply to your case. I would also separate the codes that configures the hardware from the codes that implements the Video for Linux API. Mostly because when I am reviewing other people's code, I don't really know the hardware, so I wouldn't know if the register that you are writing to is the correct one. So if they're well separated, doesn't need to be in different files. It could be just in different sections inside a single file. I can focus on the Video for Linux implementation for review. Also, I recommend removing all the code that you're not using or that you can't test. For example, the RK ISP1 driver also supports the RK3399 SoC, but I wasn't using it, I wasn't testing it, so I just remove it, but keep the code in a way that is extendable. It's easy to put the support back. Also, the driver, the PHY part, it had support for all the MIPI DPHY CSI ports, and it also had a support for the DSI port. And I was not using this one, and most of the hardware that I saw, most of the boards, were also using just a single port. So just remove everything. The code was already huge, so the idea is to simplify the code, but keep it extendable. We also had lots of macros in the headers, a lot of headers, small headers, that was not that easy to navigate. Several macros that were not being used, So just remove everything, make it smaller and easier to review. Now let's talk about this specific project, the Libcamera one from user space. As we can see, not all features are auto-discoverable from user space. An example is the RK ISP1 driver that we can select a subrectangle for cropping or a subrectangle for the image stabilizer. And in the media API, there's no way for user space to know that this subrectangle represents a cropping or the image stabilizer, which means that the driver in user space needs to know a little bit about the driver in the kernel. Also, the metadata buffer structures that we have in the statistics and also in parameters are usually in some kind of format that is very specific to the specific driver. This means that it requires user space to have specific implementations for specific drivers. So this means that we would have a specific application for a specific hardware, and the problem is that code is not very reusable. It is very hard to test since you need a specific implementation. You cannot get a generic one, a generic application, and usually those applications are proprietary. That's where Libcamera comes in. So Libcamera is an open source camera stack for many platforms with a core user space library. It has user space drivers that has the knowledge of those specific drivers on the kernel. And it also have ways for image processing algorithms that knows how to deal with the parameter and statistics. And what is nice is that Libcamera allows you to plug your own image processing algorithms as a plugin, so you can plug your proprietary algorithm, and it separates really nicely the open source part from the proprietary part. We can think Libcamera as the equivalent of the Mesa project for the graphics world, but for the camera world. Here is the architecture of Libcamera that you can see under the Libcamera docs. I'm not going to pass through all those blocks, I just want to mention some specific parts. So down there we can see the MC and video frontend support block, MC for media controller. So this is the part responsible for talking with the kernel. We can have buffer allocators, and on top we have the camera device with driver-specific code. So we have the pipeline handlers that is responsible for configuring the whole topology, and it knows which subrectangle mean cropping and which ones mean image stabilizer. We can also have image processing algorithms that allows plugins and can be proprietary. So a tip that I can give you is if you are working upstreaming an ISP, I recommend you to add, push, or update support for your hardware under the Libcamera project. It makes easier to test because sometimes configuring the whole topology is very painful. You get more users, more developers involved, since Libcamera is a very recent and very active project. People are involved in both sides, so in Libcamera and also in the kernel community. So you're probably going to receive more feedback for your driver, reviews, guidelines, design guidelines to improve the quality of your driver. And you also contribute with this awesome project. I foresee Libcamera being used everywhere in the future, so not only in our desktops, but on our phones, Chromebooks, and several devices. And that was it that I wanted to present to you. Thank you very much for watching. And feel free to reach out if you have any questions, any comments. My email address is helen.koike@collabora.com. Thank you very much.